Now you might ask yourself how we can do this same kind of test but with a single categorical set of values and compare that against theoretical or expected probabilities. And we can, and that's called a goodness of fit test. And there's lots of examples for this. A perfect place to start is asking whether a roulette wheel or a pair of dice are fair. That is, if we compared the observed outcomes of the roulette wheel or the dice, do they match the expected values close enough? Now, it's not going to be perfect. Random chance is going to ensure that there is going to be some departure from perfect expected probabilities. So we're asking the question in terms of a hypothesis test. On our TI, this is the application called fit test that we loaded on our machines. So if your TI-84 has a GOF, that is goodness of fit test with the chi-squared menu, then you do not need to use fit test. But certainly if you have an 83, then using the application fit test certainly helps. We can calculate it, we can go through the work and figure out chi-squared, but it's definitely easier with fit test. The way we use fit test is we put our observed data as a list in L2. If we're also told expected probabilities and they differ from equal probabilities, then we can put those in L1. If they're simply equal probabilities, then we do not have to put them in L1, just leave L1 blank. The program will then compute the expected counts. It'll load that into L3, and then it'll use L4 to calculate chi-squared. It then tells you the chi-squared statistic and the corresponding p-value. Here's just a quick look at what fit test is doing. It's essentially loading data into lists and then using the built-in features of the calculator. When you look at an example like babies' birthdays, we can look at, in this case, 3 different sets of samples. So we looked first at 50 random birthdays to see which day of the week they occurred on, then 300, then 1,300. And you might say it looks like some days are more common for birthdays than others. It looks like maybe Monday is a lot more common than Thursday. So we'll assume that in reality the chances of being born on any particular day is the same. That is 1/7. So we're going to look at our first example with 50 randomly selected babies. So we're assuming that the expected probability is 1/7 for each. So notice that we're leaving L1 blank. Fit test will complete it for us. We're putting in the observed frequencies in L2. Then we're going to the program menu and we're running fit test. When we do that, it tells us a bunch of information. It asks us if we have entered data or if all the proportions are equal. So in this case, we're assuming that each day is equally likely, so we enter a 1. It tells us that the chi-squared statistic is 4.88, the p-value is 0.559293751,8, and it put the expected values in L3. With our sample size of 50 babies, we got a chi-squared of 4.8 and a p-value of about 55.9%. Now, that p-value means that there's about a 56% chance of getting data, just like we did for those 50 babies, that actually correspond to the birthdays being equally likely from each of the weekdays. So in this first case with 50 babies, we'd say that there is insufficient evidence that the babies' birthdays are not equally likely on any day of the week. But we can be a little bit more sophisticated and we can see what happens when we get more data. So now let's look at 300 babies' birthdays. We now have a chi-squared of 5.62 and p is about 46.7%. Again, that could have happened simply by chance. But when we look at the data for 1,300 babies, we see something fairly remarkable. Now chi-squared is fairly large, 14.6, and p is much smaller. Now it's about 2.3% likely that we would have gotten data as extreme as that, given that babies are born equally on each day of the week. So we can say with 1,300 randomly selected babies' birthdays, we have evidence, where p is about 2.3%, that babies' birthdays were not uniformly distributed among the weekdays. We can perform so many tests with so much data that we can see a little bit more sophisticated analysis of that data. Let's look at another example, this one asking about the colors of M&Ms, a reoccurring theme in our book. The expected proportion can be found in the table. So this is what we're told the percentage of each of the colors is. So for example, if you look in the brown column, we counted out 371 out of the 2,620, but we were told that the proportion of M&Ms that are brown is 13%. And you can look at each of those columns to see the observed frequency and what we were expecting in terms of the proportion. We're asked to test at the 5% level to see if the observed frequencies actually support the claim that each of the colors occur in the proportions shown. So we're doing a hypothesis test. The null hypothesis is that the frequencies are consistent with the colors that we were told by Mars Corporation. The alternative hypothesis is that they are not consistent. Our level of significance alpha is 5%. Our first assumption is that the sample is random, but we're not told that this sample is random. Perhaps this case of M&Ms was in some way different. We're also checking that the expected frequencies for each of the colors is greater than or equal to 5. Let's go back and see that they're all at least 300, so we can be on the safe side there. Now we get out our calculator, put that data in, and we get our chi-squared, fairly large, 50.84. That tells us that p is going to be pretty darn close to 0. And so our conclusion is based on the fact that that p-value, really close to 0, is less than our alpha of 5%. So therefore, we can reject the null hypothesis. And that means that we say that there is enough evidence to show that the observed frequencies are not consistent with the distribution for M&M candies. That is, the distribution of colors is not what the company says.